This is part one of talking about Taylor polynomials and remainders. This is going to be a review of the linear case and just switching some notation in terms of what my class has seen. So we've got a function y equals f of x, and really crucial thing about all the Taylor approximation story is that you're fixing some base point a, and you're assuming that the function is simple there, its value is relatively simple. So think roughly calculate exactly without a calculator, that kind of thing. And its derivatives. And eventually we're going to want a lot of derivatives to be easily calculable there. And you want to imagine that when x goes away from a, that it's difficult to calculate exactly, or maybe just complicated, and you're going to put it into some other formula, and you really, really want to simplify it and get a really simple approximation. And the first thing you do is you use the tangent line approximation. So the linear approximation, we're going to call that the first degree Taylor polynomial. So t sub 1, often it's been called L of x before for like the linearization or something like that, but from now on we're going to call it t1 because it's in a bunch of more and more complicated approximations, higher degree polynomials, but it's just linear for now. And it's just the good old tangent line formula. And one thing that's important here is it's a constant plus, that's the value at a, plus the slope times x minus a, and we wouldn't usually need to or want to sort of distribute this factor and collect the constants and get an mx plus b. That would be, if we really wanted to know where this blue line intersected here, that would be the y-intercept, but it's unlikely that we really want that because we're only going to use this probably in some region right around a. You could do that, but it's usually fine to leave it in terms of x minus a. Now, one special case that comes up a lot is where a equals 0, and then it's not an issue, and it's going to be just a little simpler. But we want to do it in general for some base point a. So we want to say, roughly you could say the point is f of x is approximately equal to t1 of x near a. That's pretty vague. How approximately and how near? So we want to be more precise about that. So what we're going to say is, okay, f of x equals t1x plus some remainder. So you could call that the error as well. But it's just what remains once you've written down t1 of x with what remains in terms of actually getting the exact value. Or it's what needs to be added to t1 of x to get f of x. Or it's just the difference. And if you want to get it right with the notation, we want to be consistent that it's the real value minus the approximation. Or in other words, it's helpful to think of it as what you need to add to the approximation to get the real thing. We could do it opposite, but just that's not the way it's done. Okay, so that's very important. It just introduces a name, R1. It doesn't really do anything, but it lets us talk about that error as an independent thing. And then what we want is some bound on how big that error can be. So we've done that already in my class. And you have to set up just a little bit more notation. What we'd like to do is say there's some interval, and usually you do it symmetrically, like a minus d to a plus d, outside of which we're never going to go. And the advantage of declaring that we're never going to go outside of that is we get to we might be able to say something about how aggressively this curve turns away from its straight line tangent line in that region. That's going to have something to do with how big the second derivative of f can be on that region. So we bring in this d as some sort of safety fence, basically, that we're not going to go outside. And now we're going to assume that we can calculate the second derivative well enough that we can get an upper bound on the size of that guy. So this is another thing that comes in. There's some m, and this is going to come into the crucial formula in a minute. We're going to assume that the size of the second derivative is less than or equal to something that we can actually figure out. But we're only going to assume that that's true when the distance between x minus a is less than or equal to d. Or in other words, x is exactly in this region. You see a lot of stuff where you get absolute value inequalities. You can always unpack those into a chain of inequalities if you find that to be friendlier. Okay, so we're going to assume all that stuff. Okay, and that can be a little bit of a subtle issue of what do you choose for your D and how do you calculate M? How do you get some sort of upper bound? But that's more for the details than for this review. Okay, assume all that, and then I've run out of space. Well, I'll put it back up here. Okay, then our first example of an error estimate is that the size of R1 of x, as long as we stay in this region, I'll put that in a second, is less than or equal to m over 2 times the square of how far you went away from the base point. Notice that when x is equal to a, we should get exact value because it does touch there. And as x goes away from a, this number gets bigger, and that says we have less and less knowledge, less and less control of our error, which makes sense. It also says that the bigger, the less control we have of our second derivative, bigger m means that we don't know as much about the second derivative. We can't bound it as tightly. That's going to cause more uncertainty in how much this function could bend away from a straight line. And I just need to finish the statement for all x. Again, this is all happening in that safety zone. And so the D is going to be something that comes into a lot of these calculations. So what we're going to see in the videos after this is what happens if we allow our approximation to be a little more complicated. The next stage would be a quadratic function, which is not a super complicated function. It can be really, really useful. And can we get some sort of similar statement about the remainder, the difference between the actual function and the quadratic approximation? But that ends this quick review.